Okay, so the first thing I'm going to do, I'm going to gather all my cosines to one side. I'm going to move them to the side where we have more of them, so they'll be positive. So I'm going to subtract 18 cosine 2x from both sides. That'll cancel and give me 13 cosine 2x. Okay, I'm going to add 54 to both sides. That gives me -4. I'm going to divide both sides by 13, and that gives me cosine 2x equals -4 over 13. Cosine 2x equals -4 over 13. Remember the equal signs, they are equal, so I can switch which side I have those on. So -4 over 13 equals cosine 2x, or cosine 2x equals -4 over 13. Either way, we're okay there. All right, so -4 over 13 is not one I recognize from the unit circle, but I am still going to consider what quadrants that would fall in. My cosine is negative, and so cosine is negative in quadrants 2 and 3. Cosine is my x-coordinate, so x-coordinates are negative in quadrants 2 and 3. Thanks for letting me know that you're here, Jisoo. I'll go ahead and update your attendance. We're doing a problem from Delta Math that there was a question on, so you can just kind of follow along with us now. Or let me show you that. It's double angle problem, so you might want to watch. If not, let me show you, Jisoo, real quickly the code to get you in the Pear Deck. It's CGAELF, CGAELF, and it's self-paced right now, so you can go through and look at the review problems and then pick which ones you'd like us to go over. Okay, so that's what we're doing. Code's up there in the corner, CGAELF. Okay, and if she needs that again in the chat, please somebody help her with that if she needs that. Okay, so I know that I'm going to get answers in quadrants 2 and 3, but I just got to find my reference angle so that I can actually find it. So I'm going to look for my reference angle. I'm going to find my reference angle. Inverse finds angle. So I'm going to do cosine inverse of, and even though this fraction is negative, we always do the inverse of the positive so that we can find the reference angle. So I'm going to do positive cosine inverse of +4 over 13. And I'm going to make sure my calculator's in degree mode. So let's go look at that. Okay, so check your mode. Remember, by default, it's going to be in radians, so you've got to change it to degrees, okay? And then we're doing cosine inverse. I think it was 4 over 13. Okay, rounding to 1 decimal place, so I get 72.1 degrees. Is that what you got, Alice? Okay. Yes, good. Okay, so far so good. Okay, and so I'm expecting answers in quadrant 2 and in quadrant 3. And when I take a look at my expression, I notice that this is cosine of 2x. Okay, so what I'm finding here is I'm finding out what 2x equals. Okay, so do you remember the rule for finding your angle in quadrant 2? How do we use the reference angle to find our angle in quadrant 2? Well, so that's going to be going backwards from the x-axis, negative x-axis, to get into quadrant 2. So that's 180 minus the reference angle, minus 72.1. So that gives me 2x equals, or is approximately, either way is okay. That's going to be 107.9. Okay, and the rule for quadrant 3, how do we get into quadrant 3 using our reference angle there? That's going to be 180 plus the reference angle, so 180 plus 72.1, or 2x equals 252.1 degrees. Okay, now I noticed when I was working this was 2x. This was 2x and not regular x. So that makes me go back and look at my window. I put theta. I forgot the problem was in terms of x, so I'll change that to an x. So we're looking for all of the x's between 0 and 360. So where do I want to look for 2x between? What will 2x be between if x is between 0 and 360? Well, we just double that. Double 0 is still 0. And double 360 is going to be 720. So we've got to go all the way up to 720 degrees So we're going to have to go not only our first time around the circle, but another full circle forward or a second time around. Okay, so these are my two answers from the first time around. Around the unit circle. And I'm going to need to go a second time around the unit circle. Or just around the circle. To get my second set of answers so that I get all the way up to 720. So what we're looking for is we're looking for the coterminal angles, the angles that end in the same place. Okay, so they come that original distance and then another full circle more. And so we find coterminal angles by adding or subtracting 360 degrees if we're in degrees. So coterminal angles, this time we're going to add because we want to go forward all the way to 720. So we're going to add 360 degrees. It's nice with degrees because you're more likely to be able to do that in your head. So let's see if we can. So my coterminal angle with my second quadrant answer is going to be 2x equals, and if I add 360, I get 467.9 degrees, just adding 360 to get the coterminal angle from quadrant 2. My coterminal angle from quadrant 3 is going to be 2x equals 252 plus 360. I'm going to just do it in my head there. 6, that'll be 1 carry the 1. So that's 612.1 degrees. Is that what you got? Okay, help me if I make a mistake at the board. Okay. So far, so good, Alice? Okay, so one thing I want to point out, one thing that's really important here. Notice that when I got the coterminal angles, I did it before I solved for x. So I didn't divide by 2 and then add the 360 to it, okay? Because what we're doing here is we're looking for the values where 2x is that, okay? So I'm keeping it in the 2x format, okay? And now the last step that we have is now we do want to find out what x actually equals. So I'm going to divide both sides by 2. That cancels and gives me x equals 53.95, and then that's going to round up to 54 if we're doing one decimal place. So that's going to be 54 degrees. Okay, I'm going to divide both sides by 2. That's going to give me x equals 126.1 when I round to one decimal place. Okay, divide both sides by 2. Gives me x equals 233.95, and then that's going to round up to 234. degrees, and then divide both sides by 2, and that's going to be 306.1 when I round to one decimal place. Okay, and then final step, we want to put them in order from smallest to largest, and so we would just rewrite them in order from smallest to largest: 54, 126.1, 234, and 306.1. Okay, so that was a great little review problem, and let us see double angle problems. Okay, follow-up questions on that, Alice? Did you find your mistake? Something easy at the end? Questions from anybody else on that one? Like I said, it's a good one to review. I definitely put some double angle ones in the review slides because I wanted us to review one like that, so it was good to take a look at that. Any questions from anyone else on Delta Math on homework questions? Any questions from Delta Math? And so, like, I don't always ask that at the beginning of every class period, but you can always interrupt and say, hey, Ms. Weaver, I have a question from the Delta Math from last time. Like, I'll always take those questions before we move on, okay? So if you've got questions, remember to ask. Okay, what about review questions? If we take a look at review questions, are there ones that you guys wanted to look at? This first one was a double angle one, almost exactly like that one we just worked, so I'd rather not go through that again since it's just like this one. If you wanted to, though, I do have it there in the answer key spot. I have another double angle one further in if we wanted to do that. Number 3, Ashley, you got it. Let's take a look. So it's self-paced now, so me moving forward to 3 doesn't move you forward to 3, but if you want to join us on slide 3, and let's give it a try. Let's see how we do. Okay, Ashley, so you get to help me with this problem. So let's get started with it, and when you get stuck, then I'll tag in and help, okay? So what do you see? What are you thinking when you first start this problem, Ashley? Or do our problems start right at the very beginning? What do you see? What do you think?
At the beginning,
Oh, sorry. Let me turn my volume way up. Try that again.
Pretty much at the beginning.
Okay. Okay. So what do you spy with your algebra eyes? What do you see? What are you thinking? Okay. What I see is that we have secant squared and we have tangent. And that's a problem because usually if we have something squared and then a plain something and then a constant, we can factor if they're all the same function. But these aren't all the same function. I do notice that my secant is squared, and anytime I have my squareds, I consider my Pythagorean identities. Okay, so I'm considering those identities. What does our Pythagorean identity look like that has secant squared in it? Do you have those handy? If not, you want to write them at the top of your page. Remember the one I said I always remember is sine squared theta plus cosine squared theta equals 1. And then I can just divide through by sine squared theta, and that gives me 1 plus cotangent squared theta equals secant squared theta, or no, cosecant squared theta. Let me try to do that in my head there, making mistakes. Self-correction is a good thing. Cosecant squared theta. And if I divide all the way through the original one, if I divide the original one all the way through by cosine squared theta, I get tangent squared theta plus 1 equals secant squared theta. Okay, so you can generate them yourself, or you've got them on a handy dandy identity sheet. You do need to have your identities and your formulas handy while you're working on the test today. For sure you do. Okay, so the one that has secant squared in it is the one right here. And oh, look, it's already got secant squared all by itself. So what is secant squared equal to? It's equal to tangent squared theta plus 1. And when I look at my problem, I'm like, that looks like an excellent fit, because what do we already have? We already have tangents. Okay, so I'm going to consider doing a Pythagorean substitution here. So we're going to substitute in, for secant squared, I'm going to substitute in tangent squared theta plus 1. And then we still have the plus 4 tangent theta. And I'm going to subtract 22 from both sides to get that 22 on the same side so that it can all be equal to 0. Because I'm guessing I'm going to want to factor this when we get ready to go. Okay. Are we okay so far? Questions so far from anybody? Okay, I'm going to erase the scratch work here on the side with the Pythagorean identities just so that we have more room and can solve them. For you guys, remember, like I just mentioned it, but just to remind you, your identity formula chart, if you do need it, okay, is in Schoology under your identities unit, day 1. Okay, so you can go back to the unit 9, go back to day 1, and in the identities unit, day 1 is the trig formula sheet with the unit circle. And that's got your Pythagorean identities and your double angles and all those good things. Okay, so that's where you can find it in Schoology if you don't have it handy. Okay, so Ashley, can you help me from here? What should we do next?
So from here, could we just factor it?
Yeah, let's get it ready to factor. Let's go ahead and combine like terms first. Okay, what's that going to look like?
That will be tangent squared theta plus 4 tangent theta minus 21 equals 0.
Perfect. Now, one thing I want to point out, in this problem, there was no coefficient on the secant squared, so we just substituted in tangent squared theta plus 1. If there had been a coefficient, because in the practice on my previous day, we had one with a coefficient, remember that you would have to distribute it to everything in that expression that's substituted in for secant squared theta. But this one didn't have a coefficient, it was just a plain secant squared, so we just substituted in tangent squared theta plus 1. Okay, so can you help me factor this? What is this going to factor to?
Let's see.
There's only one option for tangent squared theta. That's got to break down to tangent theta and tangent theta, so I'll start there. And then if it's going to multiply and make a negative, one has to be positive and one has to be negative. Okay. So then we're just looking for factors of 21. When the signs are different, they have to have a difference of the middle term, so a difference of 4. So factors of 21 with a difference of 4.
Positive 7 and negative 3.
Okay, very nice. Now you already thought about the signs. Usually I think about them at this point, 7 and 3 are 4 apart. I want the bigger one positive so that my middle term is positive. So it's going to be plus 7 and minus 3. And I think that's what you said, which was perfect. Okay. All right. If this times this equals 0, then one of two things must be true. Either tangent theta plus 7 equals 0, or tangent theta minus 3 equals 0. So we just set our two factors equal to 0, and then we're going to start solving them. So what should I do next, Ashley?
So for the first term there, you could subtract 7, and then tangent theta equals -7.
Okay. So where is tangent negative? Thinking about my unit circle, where is tangent negative?
Quadrants 2 and 4.
Excellent, excellent. Okay. Because tangent is y over x, and the only way for it to be negative is if one of the two is negative. So that happens in 2 and 4. Okay. So we're ready to go get our reference angle. So we'll find our reference angle how?
We will take the reference angle will be the tangent inverse of +7.
Excellent. So even though it says -7, we're always going to do the inverse of the positive so that we get the reference angle in quadrant 1. So let's get our calculators real quickly. Okay, we're in degrees for this problem. So for this problem, make sure your mode is in degrees, and we are. Okay, so we're doing tan inverse. And was it just 7? Tan
Yes.
inverse 7, okay. And I get 81.9, is that what you got?
That's what I got too.
Okay, good. So it's 81.9 is our reference angle, rounding to one place. Here, we're that. Okay, so we said our answers should be in quadrants 2 and in quadrants 4. So how do we use the reference angle to find the angle in quadrant 2? What are we going to do there?
Subtract it from 180.
Okay, so theta will, because we're trying to go backwards into quadrant 2, so it's going to be 180 minus the reference angle, minus the 81.9. Okay, and so that's going to be, what is that, 168.1? Is that what you got?
I got 98.1.
180 minus 80. Oh, hello. I did 20. Thank you. That's what I get for trying to do it in my head. I was looking at the 19 and thinking 19, but no, I was in the wrong place. Okay, so what, tell me again, what did you get there?
98.1.
Yes, thank you so much. Okay, and then in quadrant 4, how are we going to get our angle?
360 divided by subtracted.
360
reference
minus the reference angle. That's right. That's right. So minus 81.9. And what did you get for that one?
278.1.
Thank you. Okay. All right. And now we have to work our other options. So that's our two options from this side in quadrants 2 and 4. Okay. What about my next option? What happens on the right side?
Adding 3, it'll be tangent theta equals 3.
Okay. And that's not one that we recognize from the unit circle. So what do we do?
We take the tangent inverse of 3, +3.
To find the reference angle, right? So I always like to label it reference angle to remind me that I'm not finding my angle itself, I'm finding the reference angle. Before I do that, let's talk about where we're looking for our answers. So where is our tangent positive, Ashley?
Quadrants 1 and 3.
Okay, it's positive in 1 and 3. Okay, so my reference angle you said is going to be tan inverse. And this time our answer is positive, so we'll do tan inverse of +3. Do you have it already?
I got 71.6.
Okay, and that sounds good to me. So to save time, I'm going to take your answer and go with it. So 71.6 degrees. Okay. All right. Now we said that we expected to get answers in quadrants 1 and quadrant 3. Okay, so in quadrant 1, how do we use the reference angle to find our angle?
It's the same.
Right, the angle itself is the reference angle. So 71.6, and in quadrant 3?
We add it to 180.
That's right. It's going to be 180, and then we move forward that reference angle, which is what gets us into quadrant 3 there. Plus 71.6, that'll be 251.6. Is that what you got?
Yes.
Excellent. Okay, then last step, we want to put them in order from smallest to largest. Now we've got our quadrants to help us, plus we can just pay attention to the numbers here. So we're going to go 71.6, 98.1, 251.6, and 278.1. Okay, so you really only had a problem with the very beginning with handling the fact that we had secant squareds and tangents in the same problem.
Yeah.
Okay, so remember, so that's excellent, right? Like you did a good job going through that problem. That means you're probably in good shape for the problem. We want to remember, have your formula sheet handy, that we are still doing Pythagorean identities. We can do double angles if we have some thetas and some two thetas. Okay, but if it's just a plain 2 theta, like most of them, then we just solve it like normal and remember to go 2 times around the unit circle. Okay, other questions or questions from anyone else on that one? Ashley ended up doing pretty well on that. Anybody else have questions on that one? Okay. What other problems would we like to look at? Does anyone have other problems we'd like to look at? I know yours may not be numbered. I think I printed yours before I numbered it, so you can tell me the problem and I can go look for it. That was for my in-person people. With the double angle. Okay, so I have, let's jump. I have another one of those further in, I think. Let's go take a look and see. So like we could do one like this. It looks easier to start off, but it is a double angle. Or would you rather go, I think number 1 was one. It's exactly like it, like the one we did. Okay, let's take a look at that other one. Okay, so this is going to be number 5 for anybody that wants to take a look at number 5 with us. Okay, so let's go ahead and give number 5 a try. Okay, so we've got secant 2 theta equals 2. So it's almost ready to solve, but it's a secant. So what do you see? What are you thinking? How can we handle that? Andriana, what should we do? Do you remember how to do reciprocal functions? Okay, so if it's equal to a whole number, we want to make it a fraction by putting it over 1. If I know the secant of 2 theta is 2 over 1, what's the reciprocal of secant? What trig function is the reciprocal of secant? Every s needs a c, so it's the one that starts with c, so that's going to be cosine. Okay, and so cosine 2 theta would be what? If secant 2 theta is 2 over 1, then cosine 2 theta would be exactly, because they're reciprocals. So they're a flip of the fraction. So it's not that we did anything mathematical to get from there to there. We just made that a fraction so that it would be easier to do the reciprocal. Okay, so if secant 2 theta is 2 over 1, then cosine 2 theta is 1 over 2. Okay, that's actually from the unit circle. So thinking about our unit circle, where is our cosine, our x value, 1/2? Where's my x value? Positive 1/2. And we are in radians this time, so that's good. So my first answer is 2 theta equals pi over 3. Okay, where else? Excellent. Okay, so right there at 5 pi over 3. So 2 theta equals 5 pi over 3. Now, when I go to write this, I notice that this is 2 theta, so it's not regular theta. And that makes me think, okay. So now notice the notation here. This is the notation you're going to see on the test. It's going to say 0 inclusive to 2 pi non-inclusive. That still is just saying that they're looking for answers, and this time our variable is theta, between 0, and it's underlined, that's why it's a bracket, because it's inclusive, and 2 pi not underlined, that's why it's a parentheses, okay? So it's still saying the same thing we're used to, they're just using interval notation. So I just want you to be comfortable when you see that on the test. Okay, so if theta needs to be between 0 and 2 pi, where should we be looking for 2 theta? What will 2 theta need to fall between? Well, it's twice as big, so the numbers are going to just be multiplied by 2 as well. 0 times 2 is still 0. 2 pi times 2 is 4 pi. So if thetas fall between 0 and 2 pi, we're looking for 2 thetas between 0 and 4 pi. So we are going to find these original 2, but then we're going to need to come and go that original amount and another full circle to find its coterminal angle. We're going to find that coterminal angle. And we find coterminal angles by adding 2 pi when we're in radians, because we go another full circle forward, okay, or by adding 360 if we're in degrees, okay? All right, so I need to add 2 pi. So this was my first time around. I'm going to label this first time around. First time around. Okay, so let's take a look. When we want to go our second time around, that's when we're going to add 2 pi to get a full circle forward. So the second time around, when I land on those same angles, but coterminal to them now, the second time around, coterminal to pi over 3, I need to add 2 pi, but to add fractions, I need a common denominator. So what does 2 pi look like over a denominator of 3? What does 2 pi look like over a denominator of 3? Right now it's over 1, okay? So to make that denominator 3, I'd have to multiply by 3. And what I do to the denominator, I'll do to the numerator. So 3 times 2 would be 6 pi over 3. Can you see that 6 pi over 3 would simplify the 2 pi? Okay, so we're going to start at pi over 3 and go a full circle forward. So pi over 3 plus 6 pi over 3 is 7 pi over 3. So my second time around, 2 theta equals 7 pi over 3. Okay, same thing for our next angle. Coterminal with 5 pi over 3, my second time around, 2 theta will be 5 pi over 3 plus 6 pi over 3, which is 11 pi over 3. And I heard a little ding on the device. Was that a question from somebody or just somebody coming in or out? Okay. If you have questions, make sure and unmute to get my attention so you're not waiting on your questions. Okay. So we've gone both times around, so we're done. It was only going 2 times as fast, so we were only expecting 2 times as many answers. So now we're ready to actually solve for theta. We know what 2 theta equals. We want to know what theta equals. So I'm just going to divide both sides by 2, which is the same as multiplying by 1/2. The 2's cancel, and I get theta equals pi over 6. I'm going to divide both sides by 2, which is the same as multiplying by 1/2. The 2's cancel, and I get theta equals 5 pi over 6. Numerator times numerator and denominator times denominator. Divide by 2, which is the same as multiplying by 1/2. 2's cancel, I get theta equals 7 pi over 6. Divide by 2, which is the same as multiplying by 1/2. And I get theta equals 11 pi over 6. Okay, we put them in order from smallest to largest for our final answer. It'd be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Okay, let's see. And just as promised or as specified by the problem, we were looking for thetas between 0 and 2 pi. 11 pi over 6 is just less than 2 pi. So all the answers we found did end up between 0 and 2 pi, just like we were looking for. Okay. Follow-up questions on that? A little more makes sense. I know we need practice, right? Like it just comes with practice. So it still may feel a little new. Okay, questions from anyone else? What problems do we want to look at from the review slides? Do you have questions on that one, Alex? Okay, just still taking a look at it. Yeah, that's fine. Okay. Okay. If there is one thing I want to talk about, but I just want to make sure and point out, if people don't have specific other questions, so let me take a look at that. Are we okay? Can I take this down? Okay, so let's take a look. Okay, this is the one that I wanted to go over. This is instructions that you're going to see on the test. And this one we actually did already. I think this was the secant squared theta plus 4 tangent theta equals 22, but I didn't point out the directions. Okay, notice that the directions said use quadratic equation to give solutions to the following over the interval from 360 to 360. So they were recommending quadratic equation as the approach to this. Okay, once we got tangent squared plus 1 in there for secant squared theta, we did not have to use quadratic equation. Even though the instructions said use quadratic equation to do it, it's still factored. And that's going to happen on the test. Every problem that comes up, because it generates different problems for different versions for you guys, they are all factorable. You don't have to use quadratic equation. We did do one of those in our notes just to show you what you would do if you ever got ones that didn't factor, but they do all factor, and I wanted to mention that to you guys. So just like we did this problem without quadratic equation on the test, even the ones that tell you to use quadratic equation, you'll be able to do them by factoring if you want. You can always use quadratic equation, it works, okay? But you won't have to use it. So I just wanted to mention that. Other than that, there's nothing in particular that I want to review. So I really need to know, are there any others you guys have questions on or want to look at? That's just undoing a square with the square root. That was using identities and then factoring. This one's just a factoring, but with harder numbers. Okay, this is the reciprocal problem we just looked at. Oh, this is a good one to look at. Let's talk about this one, okay? Because I just want to use our time. Let me see how we're doing on time. I want to make sure that everybody gets to review. Okay, we'll do this one last one together, and then I'll let you guys get working on the test, okay? So let's take a look at, this is number 6, tangent squared x equals 3. Okay, it might look like an easy problem to start with, and it's not going to be a bad problem, but tangents always require a little more work, okay? So let's go ahead and look at this problem. We undo a square with a square root. So when I take a square root, something super important happens. I pick up the plus or minus option. The square root undoes the square. That gives me tangent x equals plus or minus the square root of 3. Now, if you know your unit circle, you know that those tangent values come from the unit circle. A tangent value of positive root 3 comes from the unit circle. So this is when we should be able to get exact answers. And so how are we going to find the exact answers? Ms. Weaver's been showing you her favorite way. Okay, my favorite way is to deconstruct that tangent value to think of where that came from. So let's look at that. We know that tangent is y over x. Okay, so where did this tangent value come from? Well, root 3 would have been root 3 over 1 to make it a fraction. So far, so good. Okay, and then we know on the unit circle, all of our trig values on the unit circle have a denominator of 2. They're all over 2. So that tangent value came from a tangent with a y value of root 3 over 2 and an x value of 1/2. So I'm thinking about my unit circle. I'm thinking, now this is plus or minus, so it can be in any of the 4 quadrants. Okay, so in all 4 of my quadrants, where's my y value root 3 over 2 and my x value 1/2? Where does that happen at? You're right. That's going to happen at my pi over 3s. And because it's plus or minus, it's going to pick up all 4 quadrants. So that would be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay, so not bad, not bad. But what if you're not good at deconstructing the tangents? What is your approach going to be? Okay. Well, this is what I need to tell you right now. So I want you to work on being able to deconstruct the tangents. Like that's a good approach of being able to see the problem. But if you're not there yet and we're testing on it now, then what I want you to do before you start your test is I want you to work your way around all the angles on the unit circle, and I want you to find the tangent of each of those angles. I've shown you guys on my one here in the classroom before. I have the tangents written in on purple all the way around my unit circle. You might be able to Google it and find a unit circle that also has tangent values on it. Okay, but if you can't deconstruct it like I just showed you, you need to be able to look and see where your tangents are, where you can find those angles, okay, when we're looking for exact angles. If you do it with your calculator, if you do the tan inverse, it's going to give you a decimal approximation. It's not going to give you those exact answers. And so when it is exact from the unit circle, we want to be able to do that, okay? All right, so how would you find the angles on the unit circle? Just as a quick review on tangent. So like if I was at pi over 6, the tangent at pi over 6 would be y over x. And at pi over 6, I know my coordinates are root 3 over 2 and 1/2. So my y value would be 1/2. My x value would be root 3 over 2. When the denominators are the same, they would cancel. So that would give me 1 over root 3, which we would then have to rationalize the denominator. And that would give me root 3 over 3. Okay, so the tangent at pi over 6 would be root 3 over 3. And I would just write that next to it on the unit circle so that I would know my tangents. Okay, let's just practice a little bit together. Let's practice decomposing a few more tangents just so you can try it, okay? Because like I said, that can be an important skill. Okay, so what if I had tangent x equals -1? What if I had tangent x equals -1? That's definitely from the unit circle again. Okay, that's definitely from the unit circle. Can you decompose it and see where that happened to figure out where that happened at? Okay, so remember we said tangent is y over x. And if it's negative, what quadrants am I looking in if tangent's negative? Okay, not in quadrant 1, because in quadrant 1 everything's positive, and not in quadrant 3, just because in quadrant 3, with both a negative x and a negative of y, a negative over negative makes a positive tangent. Okay, so it's only going to be in quadrant 2 or quadrant 4, because when only one of the two is negative, that's what makes a negative tangent. Okay, so we're going to be looking in quadrants 2 and 4. Okay, now how did we get a tangent of 1? The only way for it to be 1 is if the y and the x's are the same, so they simplify down to 1. Anything over itself is 1, so it simplifies down to 1. So where in quadrant 2 are my x and y coordinates the same, but one of them's negative? That only happens at our denominator of 4 at 3 pi over 4, because that's where both our coordinates are root 2 over 2 and root 2 over 2, but one of them's negative. So this is going to be x equals 3 pi over 4 is my first answer. And it's going to be all the denominators of 4, same thing. It's going to be 7 pi over 4. Because again, at 7 pi over 4, my coordinates are both root 2 over 2 and root 2 over 2. But the y is negative, sorry, the y is negative in quadrant 4. And so would we have anything over itself? Okay, it just simplifies to 1. And so that's how we get the tangent of -1. Okay. Questions for me about that? So you can either deconstruct them and think it through, or you can just go right in your tangents all around the whole unit circle to practice it. Okay. And Ashley was right there. She knew exactly where it was going to happen, and Aditi knew which quadrants we were in. So good job with the assist from the chat, ladies. Okay, so let's try, let's see. We just did root 3 over 1. If you wanted to just real quickly deconstruct one other of those just to try it. Okay, so if I had tangent x equals root 3 over 3, that's the only other one we didn't look at. I know tangent is positive in quadrants 1 and 3, okay? And so I know, again, I know my tangent is y over x, so I'm thinking about where did this come from? Have you rationalized enough fractions to recognize this came from a 1 over root 3 that got rationalized? Can you see that? Root 3 over 3 came from a 1 over root 3 that got rationalized. All right, and we know on the unit circle, our denominators are always 2 unless we're on the quadrantal angle. So all of our denominators are 2. They just canceled because they were the same. So that's how we ended up with 1 over root 3 that then rationalized. So where on the unit circle is my y value 1/2 and my x value root 3 over 2? Where's my y value 1/2 and my x value root 3 over 2? That's at pi over 6 and at 7 pi over 6. So those would be my two answers there. So x would equal pi over 6 and 7 pi over 6. Okay, and so with a little practice, we did those during the inverse unit. When we were doing inverse trig functions, we practiced that, and that's where I first really showed it to you. But you can see it's a useful skill now that we're actually solving trig equations. But if it's still hard for you, then just go ahead and find your, it's not like you really have to go all the way around the unit circle. Once you get that the tangent at pi over 6 is root 3 over 3, then it will be for all of our denominators of 6. It's just that it'll be negative in 2 and 4, and it'll be positive in 1 and 3. Okay, so you can get those values. Okay, questions on anything else for me? Are there any others on the review you'd like to look at before we turn you guys loose to work on the test? Okay. All right, then I'm going to go ahead and let you guys start working on your test. So if you do have extra questions from the review, remember that the key to the review slides is in the folder. So in our Schoology folder for today. Okay, so in the Schoology folder for today, if I scroll up to today, we have the blank review problems and then the key to the review problems. So if there's any of those other problems from the review that you want to look at, they're in there, and I'm happy to answer questions.